Stellar evolution. Stars. They cover our night sky and power life throughout space, but at one point they weren't there. In this video, we will get into the origins of stars, how they first spawned out of almost nothing, and the importance of a star's mass on its evolutionary track. To start off, we are going to immerse ourselves in the dark depths of space, about 13 billion years ago. At this point in time, the Big Bang had just happened, and stars were just starting to form. The formation of stars arose from temperature differences and gravity. Interstellar clouds, cold yet hotter than their surrounding space, push outward against the force of gravity. When the force of gravity overwhelms the outward force of the cloud, it contracts and fragments into smaller pieces. This process will repeat and create smaller and smaller fragments for millions of years. Even though the clouds fragment several times, they are still usually over 100 times the size of our solar system. The temperature of the cloud fragments remain relatively the same throughout the multiple collapses as the heat is radiated out past the clouds and the clouds are not yet dense enough to absorb it. The density of the cloud increases very slowly over hundreds of fragmentations. With this, more temperature will be able to be kept in and the outward pressure will increase. The increase in pressure will cause the fragmentation to halt. After stage 2, an interstellar cloud fragment is usually around the size of our solar system. At this time, the core of the cloud can retain heat around 10,000 Kelvin. The density gradient of the cloud barely changes at all until we reach the core. This core now gains the name protostar. Protostars continue to gain material from surrounding cloud fragments but begin to decrease in radius due to the overwhelming force of gravity. Stage 3 marks the existence of a photosphere, the opaque surface to a star. Now, 100,000 years after the cloud fragmentation period, the core of the protostar finally reaches 1,000,000 Kelvin. At stage 4, the protostar is around the size of Mercury's orbit. Despite their low temperatures, protostars can be very luminous with their enormous amount of surface area. Protostars in stage 4 usually carry a very distinct accessory along with them, their protostellar disk. This disk is formed as the stage 3 fragments spin faster and faster, flattening out material into a disk that is around 100 AU in diameter by the time a protostar reaches stage 4. This space donut is referred to by many as a solar nebula. Planetary systems arise from this material spinning around the edges of a protostar. The temperature of the protostar, not yet enough to begin nuclear fusion, but still hot, begins to push more on the inward force of gravity and the contraction of the protostar slows. Around this time, stage 5, the protostar gets very close to the main sequence. Its luminosity has fallen to less than 10 times its previous maximum, but its core temperature has reached around 5,000,000 Kelvin. A key thing to remember about this is as the luminosity decreases, so does the contraction as the star gets denser. 10 million years after the protostar was once formed, it finally reaches a density where a temperature of 10,000,000 Kelvin is achieved, and in the core, nuclear fusion begins. The surface temperature at this stage is estimated to be around 4,500 Kelvin. Stage 6 marks the time when a protostar evolves to be a true star. In stage 7, after 30 million years, a once interstellar dust cloud reaches the main sequence. Its core temperature is about 15 million Kelvin, and at this point, pressure and gravity have finally reached a balance. This balance is called hydrostatic equilibrium. Stars like the Sun will burn their hydrogen fuel and remain on the main sequence for 10 billion years. Now you're probably wondering, what happens once all that hydrogen fuel is depleted? Well, let's get into that. So, hydrogen fuses into helium, and once that number of hydrogen atoms reaches a certain point, nuclear fusion slows. At this point, the inner core of the hydrogen shrinks drastically as it is being burned off, and the force of gravity begins to overwhelm it. The temperatures of the dying star begin to rise, and the hydrogen is burned even faster. As the nuclear fusion continues, the hydrogen burns into helium. Near the center of a star, a hydrogen shell, starting at the non-burning envelope, burns into a helium ash core. This shell is emptied of hydrogen as it is filled with helium. At the point where the hydrogen is completely depleted, gravity takes over. Gravity causes the helium core to collapse in on itself and expand outward. Stars in this stage, stage 8, are categorized as subgiants and are around 3 times the radius of stars like the Sun. A star will move horizontally to the right on the HR diagram as it becomes a subgiant. Now, on to stage 9, the phase of the red giants. Around 100 million years after being off the main sequence, a star finally reaches the status of red giant. Red giants are about 100 sun radii, and their helium core is now very small. The surface, although brighter, becomes more and more opaque. With this, stars travel vertically up the main sequence from the subgiant branch to the red giant branch. So now you're probably wondering about Earth's death. And yes, the sun will turn into a red giant and engulf the Earth and turn it to pure ash. At least we won't have to witness this fiery death. It should only be a few billion years before this happens. Anakin, this is Master Obi-Wan. It seems we have reached stage 10 in cellular development.
So the fun begins.
Sure enough, it gets very interesting here. The small yet dense helium core has finally reached 100 million Kelvin. This is hot enough to activate the nuclear fusion of helium into carbon. But there's a catch. Helium doesn't just become carbon. First, two helium come together to form a beryllium. Then, a beryllium and helium create carbon. Both of these steps release energy and make up the triple alpha process, that is helium fusing into carbon. During this process, a star can actually become stable again as its core expands from the explosive fusion of helium. This is called a helium flash. After a helium flash, stars reside on the horizontal branch of the HR diagram, as they become less luminous but rise in surface temperature as energy from the core is radiated outward. Now, around this time, the helium has just about run out, and a carbon-dominated inner core is now present. In stars with masses similar to the Sun, the carbon is non-burning. With a carbon-filled core being dormant, the force of gravity pushes it on it, causing it to shrink. At this point, there is a small carbon core inside of a helium shell, which is inside of another hydrogen shell. This second red giant phase is called the asymptotic giant branch on the HR diagram. With the intensity of the burning shells rising, more mass is contributed to the carbon core, but it isn't enough. The carbon core still shrinks, as the increasing radius of the red giant increases the pressure of gravity on the star. With more temperature, the star could fuse carbon into heavier elements, but this is only seen in high-mass stars. At peak core density, a grape-sized piece of matter would weigh in at an astonishing 1,000 kilograms on Earth. Once the star lacks the power needed to create any heavier elements, the core of the star, is officially dying. Even though a stage 12 star is on its deathbed, it can still actually increase in size. As the helium and hydrogen shells flare off, the star's radius stretches. When our sun reaches this stage, it will probably grow out to Mars. The envelopes of these dying stars pulse like a heart rate monitor. Flashes of gases cause the radius of the stars to fluctuate, and a star's matter is ejected into space. Once the envelope is pushed away, the heavy carbon core is left as a white dwarf. The presence of the white dwarf marks stage 13. At this point, we see gas clouds that were once the burning shells of a star surrounding an apparently dim white dwarf. This is the basic anatomy of a planetary nebula. We can imagine we would see something like this after the sun dies. After all, the white dwarf, the bright gleamy center of the planetary nebula, will die out. As the star ages, its white color will fade to yellow and then to red along the bottom of the HR diagram. The star is about to be buried in space for good. The pressure of gravity can do nothing more to compress the star, and as the star sheds its heat, its glow is lost, and a dark, Earth-sized spot is left to the graveyard of space. This black dwarf marks stage 14. This is the end of an average star's life. Now, let's talk about how a star's mass affects its evolutionary track. Stars with more mass tend to live shorter lifespans than stars with less mass. Stars with less mass can live for trillions of years, where the giant stars can sometimes only live for millions of years. Giant stars tend to end up having worse death than smaller stars. Giant stars explode in supernovas to sometimes form black holes. Wow, and just like that, I've sucked up 10 minutes of your life like a black hole. Thanks for watching.